Good morning, everybody, or at least this morning for me. Hope all's well. This is the last log applications lesson and my favorite. This is really cool. And before we get into it, I think it would be worth to consider the life and times of good old Newton, that is, Isaac Newton. And gravity, gravitational laws, calculus, you name it, this guy had it all going on. In fact, he was like one of the only or first scientists to be knighted. England actually appreciated his contributions, and without him, no industrial revolution, no iPhones to enjoy. The whole bit comes from the knowledge and insights, or a lot of it. Now, if not him, maybe somebody years later, but it certainly would have been delayed. So, okay. So anyway, this equation right here and the whole cooling thing isn't even in his top 10, I don't think, of accomplishments. But it's still pretty neat. So let's consider Isaac Newton. And before we just start trying to plug numbers in and how do I solve it, think about where'd this come from? What's going on in the mind of a smart guy like Isaac Newton to say, hey, I want to be able to model how fast things are cooling. And where's a good place to start? Well, I don't know. How about experiences that we have? What's your best experiences with hot stuff? I'm guessing you haven't cooked much alicha, but maybe you've baked some chocolate chip cookies, and I think I heard people say they're doing a lot more baking, whether it's cookies or bread. So let's think about it. You bake cookies, let's say you bake them at 375, and it's super hot when you take it out of the oven, so you stick it up on top of the stove. And we'll go ahead and use the lettering that's here. Notice how we're using capital T's for temperature, but then there's also a little t right here in this equation that stands for time, so we have to use both T's. I can't remember what units of time. How long will it take to stew? Does it have my units? Oh, in minutes. Time in minutes. And this is capital T. We'll assume it's in degrees Fahrenheit. Degrees Fahrenheit. Always get your units first. So if I had the situation I was talking about, where I had 375 cookies, and then there's some room temperature. Are the cookies going to cool any lower than the room temperature? No, they're going to come down and match the room temperature. So you think, well, I don't know what room temperature is. Let's say it's a perfect 72 degrees. So how is that going to look? Is it going to be a straight line? You have all kinds of equations in your bag of tricks now that you've done Algebra 2, and think through them. What are the equations you've learned over time? Last year you learned linear. And then you did exponentials this year and some quadratics. This year you've done quadratics, cubics, etc., rationals, you name it. But if we think about this, I mean, is it going to just go boom straight down and then it's going to be like that? Probably not, because what would cause this to happen? Why would it go straight down in a linear fashion and then have this sharp angle be back to room temperature? So that doesn't make sense. It could be some kind of a quadratic thing, but is it going to go down and then go back up again? No, so quadratic doesn't work. Now, if you think about this, what is good old Isaac Newton saying it is? E to the negative RT. Well, let's think about this. It looks like an exponential because there's an RT thing here. So if I think about y equals a times 1, well, what form of it should I use? A times some base to the x minus h plus k. Remember the whole left and right translations thing, and then there's a base, and then there's an a, and if base is less than 1, it becomes decay. So what's the base here? E is 2.71, blah, 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 blah. But negative, doesn't the negative power mean it's basically e to the negative? Well, I should say 1 over e. That'll be easier way to say it. 1 over e to the RT power. Isn't this saying the same thing as 1 over e to the RT power? So this looks to be exponential decay. And indeed it is. So what it's saying is there's going to be some drop in temperature over time, and it's going to exponentially decay down to that. So you take your cookies out of the oven, it's going to drop temperature really fast because the temperature differential is big. And this has the differential temperature here has implications on the efficiency of turbines that generate our power, the engine in your car, you name it. All the stuff derives from some of the basic thermodynamics that are in this rule right here. Anyway, it's going to drop fast. So maybe after 5-10 minutes you could actually pick up the cookie sheet with your hands, but you come back after an hour and a half, it's still going to be warm to the touch because it slows down the cooling as it gets the temperature of the cookie sheet gets closer to the temperature of the room. It's not losing as many calories of heat per minute per hour as it was up at the top. So that kind of all matches the reality we see. All right. So let's start filling in this equation here. I'm going to write down, here's T. So let's write down T equals, what color am I? I'm blue, that's fine. T naught TR, let's start putting maybe some color coding boxes around here. I'll use green. T naught, what does T naught stand for? The initial temperature of the substance. What is the initial temperature here? It looks like it was 212. Okay. R, what does R stand for? TR is room temperature. I'll put that in red. Hey, we'll have a Christmas thing. So that'll be the TR here. We'll plug that in. What is my room temperature? 76. It's way over there. Notice how I'm finding all these parts and pieces that I'll plug in. E is a constant. E to the negative R. So R, I'll do it in pink. R is going to be pink right there. And it looks like that old room temperature comes back again. So let me just plug numbers in. Do I have time to color code them? It might take too well, but T naught 212 minus TR is 76. E, do that in blue, to the negative 0.046, pink, 0.046, and then T, and then plus TR, 76. Now what is this plus 76 doing? Well, that's setting my baseline temperature. Isn't that a vertical shift though? Isn't that simply going to raise the, oh, I had 72 before. That's a relatively warm room. Kind of want to cool it down. 76. What will that create on my graph? Hopefully you said asymptote. And it looks like they were 212 when they come off the stove, which makes sense, it's boiling. So this initial temperature here is 212 for the Elytra, and the graph should look something like that. Okay, how long will it take to serving temperature of 100? Now this is a very practical application. Now, of course, people who cook all the time just know it because they've done it before and they can sense the temperature and the time. They know how many minutes they need to pull it off the stove. But for us, we don't know that. So I want a serving temperature 100. Sounds to me like, do I have another color left? Anyway, make it green. 100 degrees, I'm going to plug right in there. Now if I do that, I will have, well, make that 100 equals, I don't want to rewrite the whole thing. Now when I'm solving, I'll subtract. I'm going to solve, I got to get t, little t time, all by itself. So hopefully you can do that. Hit pause, solve it, see if you can do this. Don't wait and just listen to me. If you know how to do something, do it. And then I'll get there soon. Okay, well I'm going to proceed. 100 minus 76, that seems to me like 24. I'll do this in purple. 24 equals 212 minus 76, that's 88. Well, let's see, what is that? 136. E to the negative 0.046 t. Now that looks a little bit better. Actually, I should probably divide by 136. Get my E all by itself. Alright, so that's nice. Now, what's the best thing to do to both sides? Could I take log base 10 of both sides? Yes, I could. But remember, E goes with natural log. And so if I natural log both sides, blue. What will stand out? Purple. No. Green will stand out. If I natural log both sides, don't forget natural log is the same as log base E. It means the same thing. And if I log base E, this E to the negative 0.046t, they cancel each other out in the properties of logs. So that then goes to, I'll just write it over to the side, negative 0.046t is equal to natural log of 24 over 136. And if you calculate that out, you should get t is equal to 37.7 minutes. Nice. Okay. Well, how about this? Cooling rate. This one's a little bit different. We got to actually solve for our cooling rate. So try to set this equation. Use the equation up above. I'll try to use the same colors, the green, the purple, and the red and stuff like that. See what you can do to use this data to set it up in this equation and see what you get. And then hit pause and then come back and I'll proceed. Okay. I'm going. When they come out of the oven, it looks like the T0 is this 350 in green right here. Check them 3 minutes later, the cookies are 110. Okay, that's interesting. It looks like that's the temperature at some point in time in the future. Did I allocate a color to it? It looks like if I put a blue around my original equation, they cool down to 110, and that's the temperature at some point in the future where this T is 3 minutes. Little t, that is. This little t, 3 minutes up in the thing, if you can see my mouse. Violet, be quiet. Your kitchen has a constant room temperature of 78. Violet, stop barking. So that is my Violet. Shh, hush. Okay, that's the dog's name, by the way, the little puppy. I'm outside. Sorry, guys, but I don't want to re-record all this. She's usually not a barker. Okay, cooling rate of the cookies. Well, let's plug in everything and see where it gets us. So if I do this, I will get 110 degrees is equal to T0 350 minus TR is my 78. It doesn't seem like I have enough information, does it? E to the negative R. Now my minutes was 3 minutes, wasn't it? And this is T is in minutes, so that's nice. And then plus TR is 78. Okay, no, not 76, 78. Let's start doing some subtracting and plugging around. Let's subtract 78. That'll give me 32 is equal to 350 minus 78 is 272. And then that's e to the negative 3r. What should I do to both sides? Divide by 272. And then we see that cancels. And then we see the pattern. We should natural log both sides. And then the natural log of e to the negative 3r is simply negative 3r. So this goes over here. Negative 3r equals natural log of 32 over 272. And you get to r equals 0.713. No, it's cool. Now, hopefully you see that this is actually, in all kinds of engineering applications, you can see the applications to doing this and why you'd want to know how long the steel ingots have to cool until there'll be a certain temperature and you can calculate it. But this is nice to be able to model the world in this way. And who knew that natural logs would be the way to do it? And again, as a hint to the future, natural logs have a lot to do with continuously changing things, like the temperature is continuously changing. It's not going at steps. It's slowly cooling from the hot to the room temperature or the ambient. And that's what calculus is all about. And calculus has a lot to do with this natural log stuff. So, What temperature will the cookies be 5 minutes after they came out of the oven? Now we have a choice. We can choose 5 minutes from, what was the initial, 350? Or, after 3 minutes, wasn't it 110? So we could do 2 minutes from 110. Either way should work. What's better? I don't know, take your pick. In a way, I like to go back to the original. So start with the original, because we know that number is good, and didn't do any calculations, but I had to use the second piece of data in order to calculate my R 0.713, so we're using that second one. So you could try it if you want to double check your work. I'll do the original way, and if you want to see that it's true that you could start and just do T is 2 minutes from 110, that might be a good check on it. Okay, so how long? Actually, should I say how long till 105, or no? We'll just do it this way. So, what temperature? And this is simply an easy way to just plug it in. T is equal to 350 minus, was it 78? E to the negative 0.713 times, now T is 5 now, right? And plus 78. I haven't actually calculated this. I did a little bit different problem last year. What does that give me? I don't know. I don't have my calculator out here. I think you can figure that out, and I'll calculate it, and then it'll pop onto the key that I write on later, so you don't have to wait for me to calculate this thing. But I'll just go ahead and do it. Let's see how smart OneNote is. 50 minus 78 raised to the negative 0.713 times 5 plus 78. It's not that smart. I don't think it did that calculation, did it? Don't know. I don't have a calculator out here. I'll get it later. See you guys. Bye.